Oh yeah, Friday. I might be down there this weekend. Hey, so I'm going to go ahead and get started. John is going to grab a sign-in sheet, so please sign that. I'm also just going to briefly review some of the things we covered last week, but then a couple other things to point out. One is that there is, in fact, a quiz. It just covers the first 3 learning units, so the first 2 weeks John Freer gave, and then my little lecture last week. You can see, I guess I ended up with, 5 little chunks, so check that out. And well, anyway, you tell them about due dates.
Well, there's one, so the first thing is if you have not been on Moodle yet, get on Moodle and check your email, and it's going to be your email probably, and that's where all the correspondence is going to go, so you need to check that, or at least get it so that it's forwarded to your other email. So a couple of you didn't. What's that?
Your Outlook email, or is there?
It's whatever email you're enrolled as a user on in Moodle is going to be what gets pumped out if we have any announcements, such as the quiz. I know that some of you use other emails, but it's just hard to try to coordinate all those different emails. So
Are you getting emails from me in your other Moodle courses? When I say, dear NRGY, whatever, yeah. So it's the same. It's
Okay.
your UM Connect or your UMontana or your UMT dot,
Yeah.
So if you're getting that, there's only, it'll be fun.
Yeah. So the quiz was originally supposed to close tonight at midnight. We'll keep it open until Thursday at midnight. And then there's part 2 of Learning Unit 2 that there was just YouTube issues. Some people were able to load it, some weren't. I think it's officially toast at this point.
Okay.
So we re-recorded it, and
Doesn't that get
Is
one
that-
or 2 to come up?
Is
yeah,
it one of these guys?
I don't think it's that one yet. I think it's still on the relay.
Okay.
But I'll do that as soon as I get done here to make sure that it gets put over there. So that's re-recorded. It's not very long. It's only about 20 minutes, but there's a lot of really good information in there on above code programs and a lot of the green building programs. So that'll be up on there as well. And we'll close that Thursday at midnight. So some of you have already done it. You're done. Don't worry about it. But the quiz will be open through that. And if you have any questions, just get with me. Not Thursday at 11:45, but early enough that we can get something to you. So, any other questions, thoughts? Anybody? So if you haven't been on Moodle yet, you need to get on there and make sure you've got the right email, because that is going to be how we communicate.
I'll send a test right now. If you're in the class and don't see your name, so here's what it looks like from the instructor's standpoint. Compose new email. Here's everybody in the section. See Todd's here. Tim's a TA. Anybody not see their name there? Is that high enough contrast? Got everyone's in there. Rain, are you in there?
Can't see any.
Yep, there you are. So typically what we'll just do is, there's that, and then I can just say test message. No need to respond, just confirming receipt of message from, what is it, CSTN? 283?
283.
Shell. So that just goes right to your UMontana email. And it sounds like if you're getting it already from other courses, then you'll get it from this one too. Is that it?
That's all I got.
Okay, all right, super, well, thanks. All right, so I'm just going to review, I think everyone was here for last week, but I'm just going to do a 5-minute review of what we covered last week, just to kind of get the ball rolling. See if there were any questions. I also wanted to mention, I'm going to be in, if anyone had like any really big physics questions, I'm going to be in Grand Rapids, Michigan, watching Neil deGrasse Tyson's talk in a month. So if something, you want to know about gravity waves or something like that, let me know. Because, I don't know, I have a lot of fun.
I did have a question for you. Japan, it's Ogasaki.
Thinking about that. Oh, yeah?
Ogasaki, Japan's got the most efficient combined cycle electrical power plant.
Okay. I'll have to check that out. Oh, so, by the way, too, if you know anything or have an interest in the energy grid in Japan, I'm actually going to be there, about a little more than a week, but I think we're going to tour Fukushima. Is it Okasaki?
Yeah.
Ogasaki.
Is it a gas turbine there?
Combined, yeah.
Okay.
Combined cycle.
Okay. We might be stopping there. We'll see. I know Japan does buy a lot of liquid natural gas. Okay. So last time we covered the difference between power and energy. We talked about the different units that energy is measured in, the different units that power is measured in. This is your equation for the relationship between energy, time, and power. We did a little example problem. I showed you whenever you're doing an engineering technology problem, you're always solving 3 problems at once. You're taking care of the numbers, the powers of 10, as well as the units. We said that an average house consumes an average American house consumes about 1 kilowatt of electricity on a continuous basis, and that ends up being 24 kilowatt hours per day. I think we then converted that into dollars too, and said, how much energy is actually in your house, how much thermal energy is in your house at a given time. And I tried to give you a pretty good graphic on the relationship between power and energy, where the power is that little black curve, and energy is all the red stuff underneath. It's basically the integral under that curve, or the summation of all of that under the curve. I showed you the 3 laws of thermodynamics, and basically what we're going to cover today actually is just another version of this first law, that you cannot create or destroy energy, and we're just going to do it from a thermal fluids standpoint. So we're just going to dig down into one specific example of the conservation of energy. I also shared with you what's a really important concept. This is typically what's taught in sophomore year engineering courses, and how engineers are taught to think about power. And I showed you that there's always an across variable and a through variable. You multiply the 2 together. In the case of mechanical systems, the across variable is either force or torque. So whether you're pushing something or spinning something, the through variable is velocity or angular velocity, how fast it's moving through space or how fast it's spinning. For electrical circuits, the across variable, as you might imagine, is the voltage, and the through variable is current. Getting into fluids, we talked about power as being a function of how much pressure you have. It's a lot like voltage, and how quickly the mass is flowing through something. And we'll see a little bit more of that in a little more detail in Bernoulli's equation, which I'm going to cover today. So this is just fluid power. Same thing if any of you are taking any of those heavy equipment courses. Same difference in your hydraulics. Right, so you just squish one place and the fluid comes out somewhere else. And then for a thermal system, we talked about enthalpy. So that's how much heat per unit mass is in your fluid, and then how quickly that fluid's flowing through there. So we're going to talk about that a little bit more today too. Did an example calculating how much thermal energy is in a house. I think we came up with 6 cents or so. Converted megajoules to cubic feet, cubic feet to 1,000 cubic feet, and came up with 6 cents of heat in your house. We're also going to touch a little bit today on air changes per minute, Later in the course, when we do our blower door test, it's going to be critical that we determine, how many times that air comes in and out of the house, or air changes per hour is another way to think of it. So if all of that hot air leaves your house every hour, you're paying 6 cents an hour. We also learned last week that it's not just convection. So for example, if I open the windows right now, let all the hot air in the room escape, that would be the heat convecting out of the room. We also learned last week that there's always conduction taking place as well as radiation. So this is just kind of one chunk of that puzzle. Talked a little bit about conduction, phonons. So I don't know, I love thinking about this, just the just molecules vibrating. And in fact, today we'll talk a little bit about the definition of temperature when we do fluids. Convection, that's just molecules moving, and then radiation, that's photon transfer. Another thing on this, and this is critical for your building energy efficiency, is to realize that different materials are transparent to different wavelengths. So, our everyday life, we're just exposed, our eyes just respond to photons that have a wavelength between 400 and 700 nanometers. That's light. The electromagnetic spectrum doesn't end. There's stuff as long or as short as you want it. In the case of windows, light photons come through the window, but the heat photons in the room typically don't go out. That's more or less the greenhouse. That's why greenhouses work the way they do. And it's also kind of our own greenhouse effect. So that's radiation. We then went through a heat transfer coefficient, and I mentioned that this right here is just thermal power. It's also listed as Q. This is K is our heat transfer coefficient. A is the area. Delta T is the change in temperature. And if you remember last time, we spent a lot of time discussing the fact that a change in temperature in Kelvin is the same as a change in temperature in Celsius, because a Celsius degree and a Kelvin degree have the same size. The absolute scales are shifted by 273, but the delta T doesn't matter. And then S, this is how thick the wall is. So we determined that if a material, do you guys remember what this is? Was that concrete, or might have been concrete? So yeah, it was either concrete or steel, but every material has its own K value. We also talked about the difference between the K value and the R value. The R value depends on how much you have, but the K value depends on what material you're talking about. Multiply the K value times the area by the delta T, look at how thick it is, and we determined that through that chunk of building, this is probably a boiler. The thing's probably pretty hot. I mean, normally you don't have a 70-degree Celsius differential between indoors and outdoors. And 98 kilowatts of heat flowing through a 1 meter squared, like out one window, is a lot. Way more than you just get in a normal building. But the same mathematics applies. So we did it again for concrete, which has, so that first one was steel, this was concrete, much lower thermal transfer coefficient, larger area, and therefore a smaller thermal loss. And there's where we looked at the relative scales of Fahrenheit, Celsius, Kelvin, and then Rankine. You don't hear that very frequently in terms of for temperature, but Rankine is the Fahrenheit equivalent to Kelvin. The degrees are just smaller. Okay, then we went through enthalpy, which is just heat density. I mentioned the fact that little h is the intensive variable, so hopefully you took a little bit of time to look up the difference between an intensive and an extensive variable. Intensive is just how intense the energy is inside a given chunk of matter. So it's measured in kilojoules per kilogram, or energy per unit mass.
Might want to raise the bar because it's half of the plank now.
Say again?
With the bar underneath of it, it's half of the plank now. Half the plank's constant.
Oh, right, yeah. I don't think we're going to worry about that, but okay, sure. And then big H is also enthalpy, but it's how much total energy. So it's probably worth writing this here. Let's write this just off to the side. Big H, which is also enthalpy, equals little h times m. So again, little h is the intensive variable, mass is the extensive variable. How much do I have? Multiply the two together, and that's how much energy is in it. And we did a little example with the Trom wall. We said if we heat up a Trom wall, 22 Kelvin, how much energy is in that guy? I guess we came up in this case with 176 megajoules total. And I guess in this case it's also worth noting, and I'll just write it like this, H equals Q. So H is enthalpy. Q is also a variable that's typically used for thermal energy when I showed you the entropy calculation, so hopefully that makes things a little simpler. All right, any questions on it? So that was physics and heat transfer we did last time. Today I just want to look at fluids. So, all right, let me pause the recording and we'll start a new one.